Okay, so this is the review for Chapter 2. Again, this review isn't exhaustive. I would look at the lecture notes. Even though we haven't finished Chapter 2, we'll finish tomorrow, Monday. I would look at the lecture notes. I would look at the problems that you did for your homework, the recitation manual, the recitation worksheets, and those example exercises in your textbook. And then I would also look at the sort of summary key concepts at the end of the chapter, make sure that you can understand and apply those concepts. So essentially at the beginning of this chapter talks about the early experiments that led to our modern understanding of chemistry. So there are kind of two major time periods. The first time period is when people were doing experiments to determine that matter was composed of atoms. So those people are Lavoisier, Joseph Proust, and John Dalton, who was the person who ultimately came up with the atomic theory. And then the other set of scientists determined that atoms were then composed of subatomic particles, protons, electrons, and neutrons. And those people were J.J. Thomson, Ernest Rutherford, and Millikan, and then James Chadwick as well. Okay, so let's talk about the early ideas that led to the atomic theory. So the first scientist that we talked about was Lavoisier. Lavoisier came up with the conservation of mass. So in a chemical reaction, matter is neither created nor destroyed. And remember that this was a principle that led to the theory. Okay, so for example, what this is telling us is that if you have 7.7 grams of sodium, I'm writing an S here, this is indicating that the sodium is in a solid state, plus 11.9 grams of chlorine gas. And this undergoes a chemical reaction to form sodium chloride, you would get 19.6 grams of sodium chloride. So the mass of the reactants is equal to the mass of the products. The next person that we talked about was Joseph Proust. So Joseph Proust came up with the law of definite proportion. So essentially all this says is that if you take a pure sample of water from the United States and you compare that to a pure sample of water from, someplace in Europe, each one of those samples by mass is going to contain the same ratio of oxygen to hydrogen atoms. And then we also talked about the law of multiple proportions. The law of multiple proportions was proposed by John Dalton. And this says that if you have two different substances that have the same atom, so if you have carbon monoxide and carbon dioxide, but you have, since they're two different substances, they have the ratio of carbon to oxygen atoms is different. If you took the ratio of carbon to oxygen for each of these samples, and then you took a ratio of that ratio, it would equal a small whole number. And we did a bunch of problems in class, but I expect you to be able to apply both the law of definite proportions and the law of multiple proportions, or at least distinguish between one another, like the clicker questions that we did in class. Okay, so these experiments led to John Dalton's atomic theory. So essentially, the atomic theory is saying that elements are composed of particles called atoms. The atoms in a particular element are identical to one another. Atoms of an element can't be changed into atoms of a different element during a chemical reaction. So this is Lavoisier's law of conservation of mass. And then compounds are formed when atoms of more than one element combine. And a given compound always has the same relative number of kinds of atoms. So after the atomic theory was established, other scientists determined that the atom was made up of protons, neutrons, and electrons. The first person we talked about in class was J.J. Thomson. J.J. Thomson did the cathode ray tube experiment, and he was able to measure the charge to mass of the charge to mass ratio of an electron. And then after J.J. Thomson, Robert Millikan did the oil drop experiment, and using J.J. Thomson's charge to mass ratio, he was able to calculate the charge of an electron, a single electron. And then, so this led people to start to think about what atoms were really composed of. And since they knew that atoms had a neutral charge, and they were able to, Millikan was able to show that there was this negative charge, that they knew that there was some positive particle there too. And so they proposed this model, the plum pudding model, sort of like blueberries suspended in a blueberry muffin. And in that model, so electrons were sort of in some sort of sphere of positive charge. And so Ernest Rutherford wanted to experimentally try to confirm this model. And so he did this experiment. This is Rutherford, called the gold foil experiment. And in the gold foil experiment, Rutherford used alpha particles, and alpha particles have a positive charge, and so they're attracted to a negative plate. And so what he did was he shot the alpha particles through a really thin gold foil. Most of the particles passed through the foil without deflection, although a few particles did deflect. And so he was able to determine that most of the volume of an atom is empty space, and that's where the electrons sort of move around a nucleus, and that there had to be some sort of nucleus that had a condensed, where there was a condensed region of positive charge. In subsequent experiments, Rutherford further confirmed that, in fact, there was a nucleus. And so he proposed the nuclear theory of the atom. So most of the atom's mass and all of its positive charge is in the nucleus. The volume of an atom is mostly empty space. And then in that empty space, that's where electrons are dispersed. And there's as many negative charges as positive charges in an atom. So overall, atoms are electrically neutral. So there's an equal number of protons and electrons in an atom. And then another person, James Chadwick, I have his picture here. James Chadwick was able to do some measurements of the nucleus and found out that there was more mass in a nucleus than the number of protons would predict, and so that there must have been some other particle there, but that particle had to have had a neutral charge. This is James Chadwick. So now we have our modern view of the atom, where we have three subatomic particles. Electrons, those have a negative charge. Electrons are in a region around the nucleus that's primarily empty space. A nucleus that has both protons and neutrons, and that is in sort of the center of the atom. And just a couple of other things while we're on this slide. Electrons, they have a very small mass. It's about negligible. And then protons and neutrons, they have the same mass, and that contributes to the overall mass of the atom. So remember when we were looking at isotopes and we were determining the number of neutrons of an atom, we never thought about the mass contribution of electrons. So electrons have a pretty negligible contribution here. So we express the masses of atoms in terms of atomic mass units, and we can abbreviate that with AMU. Now this scale is defined relative to a standard. So it's defined by assigning a mass of exactly 12 AMU to a carbon-12 atom. 1 AMU is equal to 1.660 times 10 to the minus 24 grams. And this amount is equal to about the mass of a proton or the mass of a neutron. And this allows us to talk about atoms and think about their masses in a much more easy to conceptualize way. So if you could imagine that every time we wanted to find the number of neutrons that a particular atom had, it would be really difficult if we had to write it as 1.660 times 10 to the minus 24 grams. And so if we're thinking about the scale relative to carbon, we can think of how carbon compares to other atoms on this scale. So for example, hydrogen is about 12 times less heavy than carbon. So here we have hydrogen. It has a 1.01 atomic mass, whereas carbon has a 12.00 atomic mass. Remember, because the scale is defined to carbon, relative to carbon. So what makes elements is the number of protons that they have. So for example, helium has 2 protons and carbon has 6 protons. The number of protons that an atom has is called its atomic number. And that's the number on top on the periodic table. The chemical symbol for a particular atom is given underneath the atomic number. And then remember we talked about this number here. This is the atomic weight. And then we also talked about the fact that the atomic weight is the weighted average of all of the natural abundances of carbon isotopes. So just to remind you, isotopes are atoms of an element that have the same chemical properties, but they have a different mass because they have a different number of neutrons. So for example, carbon-12, which is the most common kind of carbon, has 6 protons and 6 neutrons. Carbon-13, which is less abundant, has 6 protons and 7 neutrons. And carbon-14, which is used for radioactive dating, has 6 protons and 8 neutrons. So just to remind you guys of the notation for neutrons, you could write carbon-12 in 2 ways. You could either write carbon-12 like this, or you could write carbon-12 using this type of notation, where C, right, is the chemical symbol, 12 is the atomic mass of carbon, and 6 is the atomic number. And remember, you find the number of neutrons by subtracting the number of protons from the atomic mass. Also remember that the number of protons is equal to the number of electrons. So we were just talking about the fact that the number of protons is equal to the number of electrons. That's for a neutral atom. Atoms can also be ions, right? So in a chemical change, for example, atoms can gain or lose electrons, and they can become charged particles called ions. So something that has a positive charge, like sodium ion, is called a cation, and something that has a negative charge, such as the fluoride ion, is called an anion. So just a real quick naming convention. When things are positively charged ions, those things are mostly going to they're mostly going to be metals, but you're going to just call it the element name plus the word ion, so sodium ion. Negatively charged ions, on the other hand, so this is fluorine, that's the neutral atom, but fluoride is the negatively charged ion. So you're going to change the INE to an IDE anytime you're dealing with an anion. Okay, so you guys should have watched a video about the periodic table. You can watch that video instead of this video for a review, but just a couple things in general. The periodic table is arranged in order of increasing atomic number. Elements that have similar properties, they're in these vertical columns. We call the elements in the vertical columns groups or families. And then the elements that are in the horizontal rows, they're called periods. And so the elements that are to the left of this zigzag here, those elements are metals, with the exception of hydrogen. It's not a metal. And then the elements along this zigzag are metalloids, or semimetals. You've heard of the word, probably semiconductors, right? So those are those elements. And then on the right, you have nonmetals. So in addition to both the horizontal and vertical locations, and then the locations of metals, semimetals, and nonmetals, you have to be familiar with the name of some of the groups in the periodic table. So those groups would be 1A. 1A, those are alkali metals, so lithium, sodium, potassium, so on. And then 2A, those are the alkaline earth metals, so beryllium, magnesium, calcium, strontium, barium, so on. And group 8A, those are the noble gases. People call them rare gases sometimes, like you'll see that in older books. Those are helium, neon, argon, krypton, xenon, radon. Now, you should also know just some basic things about these elements. So like in group 8A, these are very unreactive gases. You usually find them by themselves in nature, so you can find just helium alone or neon alone. Whereas the first two that we talked about, 1A and 2A, the alkali and alkaline earth metals, they're highly reactive. So if you've ever put like sodium in water, it can have a very violent reaction, for example. In group 7A, these are halogens. So fluorine, chlorine, bromine, iodine. And halogens can either be found, they're oftentimes found as salts, or they're found as, for example, sodium chloride, or they're found bonded with each other like chlorine gas. So in addition to knowing the groups and whether or not something is a metal or a non-metal, you should know that this region here in the periodic table, these are called transition metals. You should also know that atoms ionize in a very predictable way. So we're going to be dealing with ions just pretty much for the rest of this, for the rest of Chem 109. When metals lose their electrons, they form cations. When nonmetals gain electrons, they form anions. We defined cations and anions before, but everything in group 1A is going to form a +1 cation. So it's in group 1A, so that can help you remember. If it's 1A, it's going to form a +1 ion. Things in group 2A form 2+ ions, and then aluminum in group 3A forms a 3+ ion. We're not going to talk about boron because since it's a metalloid, it's kind of a weird one. It's an exception to all the rules. So if we look at 8A, these don't form ions. 7A, they form -1 anions. And then 6A, -2, and then nitrogen, you should know as well, forms a -3 anion. The one way to remember it, we're not going to get into electron structure or anything like that, but 7A is 1 away from 8A, so these guys form a -1 ion. 6A is 2 away from 8A, so they form a 2-, and so on and so forth. Well, really just for the nitrogen ion. That might be able to help you remember. Okay, so here's the most important thing. How do you need to use this information? So I expect for people to be given a symbol of something on the periodic table, like chlorine, and then predict what ion is formed and then the number of electrons of that ion. So for example, chlorine is in 7A, so it's going to form a chloride ion. This ion has a negative charge, so it's called an anion. And then we want to find the number of electrons. So if chlorine is 17 on the periodic table, this is the number of electrons in the neutral molecule, just so we're all on the same, or the neutral atom, just so we're on the same page. The number of electrons is going to be equal to the number of protons, so 17. So let's look at the next one. So we have something Be2+, that's the ion formed. Well, Be2+, the symbol for this is Be, it's beryllium. And then if we look at the periodic table, Be is 4, so it's going to form, or it's going to have 4 protons, and then it's also going to have 4 electrons. So let's do this same thing with sulfur. So sulfur is 16 on the periodic table, so it's going to have 16 protons and 16 electrons. Let's look and try to figure out what kind of ion is going to form. So sulfur is in group 6A. 6A is 2 away from 8A, so it's going to form a -2 ion. So we're going to write S and then a 2 and a minus. In addition, I expect for you, if you see something like, I don't know, like lead 208, I expect for you to be able to determine the number of protons and the number of neutrons. So the number of protons here is 82. And then the number of neutrons is going to be equal to 208 minus 82, which is 126. If we wanted to write the carbon-12 isotope, I would expect for you to be able to write carbon-12 like this, or see carbon-12 like written like this and know what it means, or write it in this notation. I also would expect for you to be able to look at the periodic table and know which elements are going to be the most similar. So if I said, out of these elements, which is most similar to chlorine? Chlorine is in group 7A, fluorine is in group 7A, magnesium is in group 2A, and oxygen is in group 6A. So because chlorine is in group 7A, it's going to be the most similar to fluorine, which is also in group 7A. So I expect you to be able to answer questions like that. Okay, so we mentioned that on the periodic table, the atomic mass is the weighted average of the natural abundance of all of the different isotopes for a particular element. And I just want to mention that there's a machine, an instrument that allows us to, figure this out, to measure the different mass contributions and abundance of the different isotopes. And this is called a mass spectrometer. So atoms can get introduced, a sample gets put in. So let's just, we were thinking about neon in class. So neon atoms, they're introduced into the mass spectrometer. They get ionized, so they form positive ions, and then these positive ions are directed through a magnetic field. And the path of the ions of the neon sort of diverge as they pass through this field, and then we can quantify not only the sort of fractional abundances, but measure the atomic mass of these isotopes as well. So essentially, a mass spectrometer is a machine that weighs molecules and separates them by size. So if you have, actually this is how Coinstars sort of work. If you have like a pile of change and you put it in the Coinstar, it's sorting those coins by the weight and the abundance of those coins. So essentially that's what a mass spectrometer does. So if we have this pile of change and we put it in a mass spectrometer for coins, you would get two measures here. You would get an idea of how many, and then you would get an idea of how heavy. So if we put a sample of neon into a mass spectrometer, you would get 3 peaks of neon, because there's 3 neon isotopes. Remember we talked about it in class. We said that there was neon 20, we said that there was neon 21, and then there was also neon 22. So the mass spec gives us the percent abundance of each one of these isotopes, and then we use that information to calculate the weighted average that's on the periodic table. Okay, so the very last thing we need to talk about in Chapter 2 is this idea of Avogadro's number and the mole. So in chemistry, the counting unit that we use for counting anything, for counting atoms, for counting molecules, ions, whatever, is the mole. The mole is abbreviated MOL. 1 mole is equal to 6.022 times 10 to the 23 particles. We use this number just like we'd use a dozen eggs. So 12 eggs is a dozen eggs. Similarly, a mole is 6.022 times 10 to the 23. Now, we base this idea of the mole off of the number of atoms in exactly 12 grams of pure carbon-12. And so we have that 12 grams of carbon is equal to 1 mole of carbon atoms. 1 mole of carbon atoms is equal to 6.022 times 10 to the 23 carbon atoms. So this is essentially telling us that the atomic weight of an element in atomic mass units is numerically equal to the mass in grams of 1 mole of that element. So this example that we were just talking about right here, we were just talking about carbon-12. So carbon-12, the AMU for carbon-12 is 12. But on the periodic table, we have the weighted average, right? So I drew a little picture of carbon on the periodic table here. So if we look at the atomic weight, here, 12.01, is going to be equal to the mass in grams of 1 mole of that element. So this means that 12.01 grams of carbon is equal to 1 mole of carbon. And we call this 12.01 grams of carbon for every mole of carbon. We call this the molar mass. And so I think that you've probably heard of that and used that quantity when you were in high school. But I'm going to expect for people to be able to use molar mass and to also use Avogadro's number to solve different quantitative problems. So we're going to do some examples next. Okay, so for both molar mass and Avogadro's number, these are the kinds of problems that I expect for you to be able to solve. So let's look at the first one. The first one involves calculating the mass in grams of 0.473 moles of titanium. So you're given moles and you have to find mass in grams. So you can use molar mass as a conversion factor in order to figure this out. So you have to go to the periodic table, find titanium. Titanium is 22, in case you're trying to do this on your own. And the molar mass of titanium is equal to 47.867 grams per mole. So, in order to solve this problem, you're going to start with your given unit, right, which is moles, and then you're going to set up your conversion factor. So 0.473 moles of titanium times 47.867 grams of titanium. So one thing that's really important when you're using molar mass is that you need to label really well. So you need both the unit that you're using as well as the chemical symbol. So if you notice when I wrote this here, I have 47.867 grams of titanium over 1 mole of titanium. So please always write it like that. So now I'm going to look and see if my units cancel out, my moles cancel out. And I'm going to make this multiplication. Notice that 0.473, it has only 3 sig figs. So my answer should only have 3 sig figs. So this is 22.6 grams of titanium. And again, I wrote both the unit and the chemical symbol. Okay, so let's look at this next one. So this next one is calculating the amount of copper in moles of a 35.8 gram pure copper sheet. So this time we have grams and we want to find moles. So we're going to use molar mass again. So you're going to look on your periodic table. Copper is 63. Oops. So the molar mass of copper is 63.63 63.546 grams per mole. And again, we're going to start with our given unit. Our given unit is 35.8 grams of copper, so grams of Cu. We're going to use molar mass as a conversion factor. This time, though, grams is going to be on the bottom because we want grams to cancel out. Grams of copper for every 1 mole of copper. I want to make sure that my units cancel out, so grams of copper cancel out. So you have 35.8 divided by 63.54. 0.563 moles of copper. And again, this should have 3 sig figs. Okay, so let's look at this next problem. So we want to find the number of helium atoms in 5 grams of helium. So we have a mass of helium. Oops. And we want to find the number of atoms. Well, we know that we can go from grams of helium to moles of helium using the molar mass, and that we can relate moles of helium to the number of helium atoms. So we're going to use 2 things here. We're going to use both Avogadro's number and the molar mass of helium. So let's set this problem up. So helium is 2 on the periodic table. The molar mass of helium is, let's see, 4.0026. Grams per mole. And then remember, Avogadro's number is 6.022 times 10. Let me write that better. Times 10 to the 23 particles for every 1 mole. All right, I'm running out of room. I'm going to move this up. Okay, so let's start with what we're given. We're given 5 grams of helium. We're going to use the molar mass. We need grams to be on the bottom. 4.0026 grams of helium for every 1 mole of helium. For every 1 mole of helium atoms, we know that there are going to be 6.022 times 10 to the 23. So we're going to make sure that all of our units cancel out, our grams cancel out, our moles cancel out. We're left with helium atoms, which is what we want. 5 grams has 3 sig figs, so our answer should only have 5 sig figs. I'm going to put this in your calculator. So 5 grams of helium atoms has 7.52 times 10 to the 23rd helium atoms. Okay, finally, I wanted to include one problem where you're integrating what you learned in Chapter 1 and what you learned in Chapter 2. This would be sort of the ultimate goal so far for you to be able to solve problems like this. So this question gives you a number of atoms, and then it asks you to find the edge length of a cube. So this edge length of a cube is just one dimension in volume. So you know volume of a cube is equal to length times width times height. So we're having to go from atoms to volume. And we're given the density, so we are going to be able to use density as a conversion factor for this. But we need to think about how we can relate atoms to grams. Well, we can relate atoms to grams through the molar mass of titanium. We used titanium in a problem before. Let's look at the molar mass from the periodic table. So the molar mass of titanium is 47.87 grams per mole. And we know that if we have the number of atoms of something, we can use Avogadro's number to find the number of moles. If we know the number of moles of something, we can use the molar mass to find the number of grams. If we have the number of grams of something, we can use the density to find volume. So this is how we're going to approach this problem. So we're going to go from the number of atoms to moles, from the number of moles to grams, and from grams to volume. And then once we have the volume, then we can deal with this edge length part. Okay, so let's set this problem up. So we have 2.86 times 10 to the 23 atoms. So we need to use Avogadro's number. So for every 6.022 times 10 to the 23 atoms, and I should be writing atoms of 10. This tablet doesn't allow me a lot of room. I'm going to start writing them now, but sorry about that. For every 1 mole of 10. We have the molecular weight of 10, or the molar mass, so we can use that. We're going to have moles on the bottom for every 1 mole of 10. There's 47.87 grams of 10. I'm going to make this smaller, running out of room, times the density. So we have 4.50 grams for every 1 cubic centimeter. So let's make sure that our units cancel out. And then I'm going to also write 10 here, sorry. Okay, then we have everything properly labeled. So we're going to cross out atoms, we're going to cross out moles, we're going to cross out grams, and so we've gone from atoms to volume. All right, so we're going to put that into the calculator. All right, and I get 5.052 cubic centimeters of 10. All right, so if volume, and this isn't in the correct sig figs, we'll deal with that in just a second. So if volume is length times width times height, we want the dimension, we want the length of one edge of this cube. So we're going to take a cubic root of this number here in order to find that, that edge length. So in your calculator, there's not a cubic root function. And so if you take 5.052 and if you raise it to the 1/3 power, that's the same as taking the cubic root. Okay, I'm going to make all this smaller. So the edge length of this cube is going to be 1.72 centimeters. And we have 3 sig figs because we're limited by density, and density has just 3 sig figs. Okay, so if you're really nailing this material, this is the kind of problem that you should be able to solve. Okay, so just expectations for Chapter 2. I forgot to put a slide like I did for Chapter 1, but I expect for you to be able to sort of describe what experiments led to the atomic theory proposed by Dalton. So the law of conservation of mass, definite proportions, multiple proportions. And then just basically describe, not in great detail, but be able to at least associate the correct experiment with the correct scientist for the early experiments that led to the nuclear theory of matter. So like that J.J. Thomson, he did the cathode ray tube, and he found the mass to charge ratio for an electron, that sort of thing. Be familiar with what an atomic mass unit is, the chemical notation, the notation for atomic number, chemical symbols, and that sort of thing. Know the periodic table, know what groups are, know where the metals are, the non-metals, the transition metals, and that sort of thing. Be able to predict what kind of ions a particular element will form. And then be able to use Avogadro's number and molar mass in order to solve quantitative problems. And if you have any questions about this, ask in class on either Monday or Wednesday.